Hey, all. Today we're going to continue talking about hypothesis tests. We're going to talk about our next kind of hypothesis test, sticking with proportions, but now with two proportions, kind of like we did with confidence intervals. So we still need to maintain the same structure of a test, just like we always maintain the same structure of a confidence interval when we did an interval for a different parameter. And so we always have our null hypothesis and our alternative. And so reminder, there's our null, there's our alternative. Our null is still going to be an equality. In this instance, our null is always going to be equal to 0. We are always going to assume there is no difference in the proportion of these two samples. And so we take sample or population proportion 1 minus population proportion 2 is 0. This means there is no difference. For our alternative, we are going to pick an inequality. So one of them is bigger than the other, or just straight up they are not equal to each other, the two-tailed test. And so remember that we always assume the null hypothesis is true until we establish that there's enough evidence that it's not. And so we're assuming here that there's no difference in these two populations. And so if we were to try and find a standard error for the difference of populations that have no difference, it would be kind of, it just wouldn't work, basically. I'm having a hard time finding my word, but it wouldn't work. And so what we do is we come up with this pooled p hat and pooled q hat. And you might not need to calculate this except for maybe on a multiple choice question at some point. But what we do is we combine the successes, so x1 and x2, and we combine the sample sizes, and we create one proportion of successes, one p hat where we pool them all together, put them all together, and then we can find q hat pooled the same way we'd always find q hat, subtracting from 1. And so the standard error formula looks similar to what we had for a confidence interval, except now we're not using two different P's and Q's. We're using the same one, this one that we created from the pool. Yeah, and that's the difference here from when we had a confidence interval. Your calculator will do that for you. This is something that you might just need to be able to manipulate for like a multiple choice question on an AP practice or the AP test. Our assumptions and conditions are the same as we would have seen for confidence intervals. We always need a random sample. You need to make sure that you're establishing that we have acquired our information through random methods or random assignment in the event of an experiment. We need independence. We need all the individuals in each group to be independent. We need the groups to be independent of each other, meaning one group is not influencing the other group. And usually how we establish that, of course, is by saying, hey, we've sampled less than 10% of the population. If we have sampled more than 10% of the population, we'll run into a problem. And then we want to establish the normal model is appropriate by doing an NP times NQ. And of course, we can't do, oh yeah, we can. I'm sorry. We're going to do this for both groups. But we're not going to use like a null p because our null hypothesis is 0. So what we're going to do is we're going to make sure we have enough successes and failures in our sample. So I finally went and fixed this to be P0, Q0, and we didn't need it. So we're going to do this for both groups, make sure we have enough successes and failures in our sample. So take a minute and read through this one. And I'm going to document some of the important things, and then we'll run a hypothesis test for two groups here. So I like to write down all the stuff I have. We're talking about looking at patients who have cardiac disease, and we want to know if there is some effect that depression might have on whether or not they survive their cardiac disease. And so we have two groups, a group of cardiac patients that have been diagnosed with depression and a group of cardiac patients that have been diagnosed to not be depressed. And so they told us the total number in each group and then the total number of people who died. So those are our NPs or our X's. are unfortunately in this case successes. That's kind of a sad way to say successes. And so then our NQs are failures, people who lived. Again, not really, doesn't really make sense practically, but in this case, a failure is somebody who lived. There were 63 who were with depression and 294 without depression. And so what we want to know is, do we have evidence from our sample, from our observational study, um, to say that there's evidence to show that there is some difference in these two groups, meaning that depression has some sort of relationship with whether or not you survive your cardiac disease. So let's set up our null and alternative hypothesis. Our null hypothesis is going to be that there is no difference. And so let's call without depression, we'll call that P1. With depression, we'll call that P2. And if you call that out, you can follow through using P1 and P2 without some creative like P depression, P no depression. And so we want to know, are depressed patients more likely to die than non-depressed patients? So we need to set up our alternative. And so we want to know if the proportion of non-depression or of depressed patients is bigger. So we are going to have our inequality eating the bigger side, which here is the proportion of depressed patients. Now you can set this up differently. If you made depressed patients P1 and without depression P2, you would have a different inequality. We'll still get the same results. We'll still make the same interpretation. Just make sure that you know P1, which one is P1, which one's P2. We want to establish our alpha, our significance level right off the top. Since we're not specified, we're going to use 0.05. That's what we're going to compare our p-value to at the end. And so what we want to do is run a two-proportion z-test. And we're going to use our calculator. We need to make sure our assumptions and conditions are met. We do have, we don't really have random assignment here because we're not assigning patients to be depressed or not be depressed. This is an observational study. What we can say is that these 450 people are probably representative of people who have cardiac disease. So we can cover that using that assumption. I would say 450 people is less than 10% of the population that might have cardiac disease. Also, these patients and their cardiac disease are not probably influencing each other. And I would say that the two groups are independent. Our cardiac patients who are depressed are not trying to make our cardiac patients without depression have depression. They won't be influencing each other. And then, of course, we've already kind of established NP and NQ are greater than or equal to 10. We have those numbers here. So if you do that documentation off the front, you can establish that condition pretty quickly. Again, I'm not writing these down here because I want to focus more on the test because we've been doing assumptions and conditions for quite some time now. But you need to make sure that when you're doing this problem or doing a problem like this on your own, you are actually documenting those assumptions and conditions, especially when it comes to a test, because it's what establishes that we're allowed to do this. So let's go and find the test on the calculator. We're going to do a two-proportion z-test. And I said that my first group, P1, is those without depression, so I'll put in my information there. And again, if I have that all documented, I can just grab it and put it into my calculator. Group 2 is my depressed patients. Oops. And of course, make sure you're putting the numbers in the right spot. And then we need to pick the correct test. So we're going to look at our inequality that we wrote, and we're going to choose the one that looks just like it. We're doing a one-tailed test here. So left-tailed test because we have a less than. So if we were to draw some sort of representation of that, This is something good that shows to the person reading your test that you know what's going on. Of course, we could always calculate a z. Um, there's our, we're going to have a p-hat difference because we're going to have a sample difference here of our proportions. So what we're trying to do is find the probability that if there really is no difference in our sample proportions, what's the probability that we get our difference? I'm sorry, if there's no true difference in these two groups' populations, what's the probability that we get this sample difference or a sample difference that is more extreme? And so we're just going to do that on the calculator. And I want to write this notation. I'm going to find the probability that our sample difference is less than, and we should actually find that sample difference. So let me go calculate p-hats real quick. So if I calculate my p-hats, I do get a bigger p-hat, bigger sample proportion for my deaths with depression. Probably thinking about this again, I might have done depression minus without depression to not get a negative number, but that's all right. So we want to know the probability that our sample difference is less than what we got. And so again, let me go back to a function on the calculator. It's choice 6, 2 proportion z-test. I should have all my stuff in there still. Make sure if you have to go back through and you're entering all the way down, you don't accidentally choose the not equals to, because you're going to get a bigger number than you should. And then we can calculate. It'll tell us our two p-hats, which we just found. It gives us a p-hat pooled. That's what that is right there. It's adding the two x's and dividing by the sum of the two sample sizes. So that's what this other p-hat is, p-hat pooled. And then this plain p, that's our p-value, our probability, 0.0131. And so what we need to do is compare that to our alpha value. And I kind of like to do this. Write it out. We have that table from the last lesson. My p-value is 0.0131. My alpha is 0.05. We established that before we did the test. And we need to figure out which one's bigger. If you remember, the inequality eats the bigger number. So our p-value is less than our alpha. And so if you were to look at that chart, which eventually you're going to have to know, but you can use it now as a guide. If you were to look at that chart, that would tell us to reject the null hypothesis. This means that only about 1% of the time, there's only about a 1% chance that we actually get this sample difference of 0.1. There's only a 1% chance of getting that sample difference from our observational study if the true difference is 0. 1% is so small. This shows us that we have great evidence that the true difference in cardiac patients who die who have depression and cardiac patients who die who don't have depression is not 0. There is a difference. This depression is playing some role in whether or not you survive your cardiac disease. And so we will reject the null hypothesis. This is like saying, hey, you're guilty. We're rejecting your innocence. And we're going to say we have enough evidence to make this conclusion. And I like to steal my conclusion from the question. It helps you get the context into your conclusion. And so I'm going to do that. Always note your p-value, always note your alpha value, always note your parameter of interest. And so let me write that up and then we'll talk about it. So here we're stating our p-value that we calculated. We're stating the alpha value that we established at the beginning of our test. Because we rejected the null hypothesis, we have enough evidence to show this thing. So we're going to say we have enough evidence. You don't need to state in there that we've rejected the null hypothesis. This is a result of rejecting it. And then we want to, say, what does this show? Well, it shows that depressed patients with cardiac disease are more likely to die than non-depressed patients. And so what this could do is this can open up an opportunity for doctors to work on a cardiac patient's mental state to try and improve their ability to survive their cardiac disease. Um, this is important information, and so this research would be helpful in that. Of course, there's going to be questions here at the end about this problem. Do make sure you watch all the way to the end. If you do have questions, as always, raise your hand, ask me. I'm more than happy to help, more than happy to talk more about statistics. Um, Make sure you do practice, because this is just the first step in mastering this idea. You need to do the practice. You need to ask for help if you're stuck, and I wish you luck.